So the player has a choice between numerous different styles of throw, including they can control the speed, the angle of throw, and whether it's backhand and forehand. So an example of a forehand throw with a relatively modest angle and speed can be seen here. The ball goes out about halfway into the field. And a higher angle version of this can be seen here by pressing a different key, which will take the ball further along. In addition to that, we've got a backhand throw, which adopts a very similar power and bias to the first throw. So they end up in roughly the same location, but coming in from a different angle. But we also have a more powerful version of that backhand throw, which does similar to what our second throw did. In addition to that, we've also got a couple of wildcard throws. For instance, our J key here, which throws the ball way out on a kind of at first central angle, which could be used to disrupt balls thrown that are not as far along as others. And we can also see that things like collision are going to work fine and consistently, so balls will bounce off each other in a realistic way. And they will also transfer the right amount of speed to each other, so that collisions maintain a rough conservation of energy. There's also the option to just throw a ball straight out like this. And there's another example of the realistic collisions, as the two balls that it hit both went off at angles, as they would be expected to realistically. So my program handles collision detection using something called axis aligned bounding boxes, or AABBs. These are basically just cube-shaped areas surrounding each box. So while you can't see them, each and every one of these balls has a small box essentially hugging the surface of the sphere, and it's the lines of these boxes that determine where collision is happening. So every time we call an update thread in the program, we are checking for an overlap between collision boxes of every sphere. So for X sphere, we check with all other spheres whether X sphere's bounding box is in some way overlapping on any dimension with another sphere's bounding box, because if it is, then we know we have a collision between spheres, and we can then determine what action we need to take. The flaw with this is obviously a cube is not the same size as a sphere is, so there's going to be some inaccuracy, but the trade-off with that is that with that bit of inaccuracy, we also gain a quite big memory advantage. We're not having to store all of the vertex data to make up a collider sphere. We're only having to do it for a box. And in the case of this game, that's good enough. So to explain how the balls react with each other in more detail, we need to look at how we're mathematically defining what the new positions for a ball is when it is impacted. So the way we do this is by creating and generating a new vector based on the positions of the two balls involved in the collision. Because we don't want to do a simple thing where we just have one ball hit another and the ball that's stationary takes the heading of the attacking ball. Because that would be a very simple and kind of lackluster collision. It wouldn't account for a scenario where a ball hits another ball at an angle. What we want is, like what we see in our diagram above, the attacking ball coming in at a higher angle than the stationary ball, and as such the stationary ball taking a downwards and to the right vector when it reacts to the collision. So this is done by simply taking the position of the attacked ball and taking away from it the position of the attacking ball, and then we can normalize that vector, and what we get is the vector of our black arrow here, simply telling us that the ball that's been hit is now going to go off in this direction. Afterwards, we can create a new vector for our attacking ball that simply is a reverse of its previous heading, effectively creating a kind of bouncing off scenario. So we mimic realistic collisions for our balls without using up too much memory. We're simply doing 2 bits of maths with vector freeze. We can also demonstrate a collision between a ball and the ditch at our far right end here, because obviously if a ball comes out of play, we want it to stop in the ditch. We don't want it to keep going on forever. So here we can see our ball is being thrown far too powerfully and it's ended up in the ditch where it's come to a stop. So as we move our balls along, we can see they exhibit deceleration as they go along to mimic how they would do so in real life. So obviously the ball's going to be moving at its fastest when it's released from the hand of the player. And as it moves along the bowling green, friction with the surface and impacts of other objects are going to slow up or down. So we want an effective and convincing deceleration, which we can see exhibited here. Our balls start off quite quickly and then slow down as they move towards their finish point, slowing down especially fast if they impact with another object. And this acceleration is also present when objects are responding to being hit by another ball. So if we see one ball being hit, it will first start moving away quite quickly and then it will slow down gradually. So our deceleration is a constant thing. If our balls are moving, there'll be deceleration involved. The friction is there as if it were a realistic actual friction. So another aspect of detail to the movement of our balls is the fact that they exhibit a slight rolling motion as they move across the lawn. Obviously in real life, if you're rolling a ball, you expect it to roll, and while it's not quite fully implemented here, we can see that as the ball moves along, it does rotate. The main center logo of the ball, which is this grey area with a kind of A written in the center of it, comes more into view as it passes along because of a slight rotation as it goes along. So we do have some partially implemented rolling of the ball to add to how dynamic they are. So in terms of a conclusion about how the physics aspects of the project went, I would say on the whole pretty good. I think the strongest aspect of the project is in ball-to-ball collision. So not only do balls react to each other properly, but they also choose their headings for new vectors when they are reacting to an impact realistically. So if we have a ball hit another ball at an angle, it will take that into consideration. It won't just, send the balls off wherever. And so the result is we've got fairly convincing collisions between the balls. They act and behave and carry out collisions exactly like we'd expect them to do so in real life. And that includes also conservation of speed. So if a ball hits another really fast, they're both going to react to that very quickly and go off quite quickly. And if they react or hit each other quite slowly, then yeah, the collision is going to be a slow collision. On top of that, the deceleration is pretty convincing, especially how it works when we've got our backhand or forehand throws. The curvature on that looks pretty good. And we've also got the choice in biases there, so that means we can have a much steeper angle like that, or a much shallower one like the last one. There's also the option to just, straight out throw the ball out. So we've got a variety in terms of speed, bias, and backhand and forehand. In total we've got 8 different, or 9 different options for throwing out the ball. In terms of where the physics didn't go so well is that balls colliding with the ditch don't do so very convincingly. They just kind of stop in the middle of the ditch. And there's also no collision between balls when it comes to the ditch. So that obviously does not look very good at all. That's a pretty big flaw. And there's also the lack of any additional element. We've got friction and we've got balls colliding, but we haven't got wind or outright different types of balls. There's only one specific type of ball, and there's also no real jack. A jack can be thrown out by pressing X, but there's no clearly visually distinguishable jack, and there's certainly no jack that has any physical difference to any other ball. So that would be the biggest flaw, I'd say. But on the whole, I've got deceleration, a large choice of throw techniques, including differences in biases, speed, and backhand and forehand, and pretty convincing collision.